By the 1970s, the vacuum tube seemed to have lost the most one-sided technology war of the modern age. Transistors had taken over radios, televisions, computers, telephone networks, and nearly every other electronic device ordinary people could see. The old tubes were large, hot, fragile, power-hungry, and slow to warm up. Semiconductor chips were smaller, cheaper, cooler, and could place thousands, then millions, and eventually billions of electronic switches onto a sliver of silicon. The verdict appeared final. Vacuum tubes belonged in museums, vintage amplifiers, and memories of television repair shops. But one branch of the family never accepted the verdict. Today, descendants of a vacuum tube first made practical inside a secret British microwave laboratory during the Second World War still amplify signals in radar systems, communication satellites, deep space spacecraft, and electronic warfare equipment. In one publicly documented aircraft defense system, high-power traveling wave tubes help a decoy transmit signals intended to draw radar-guided threats away from an F/A-18 Super Hornet. This is not a forgotten glass bulb kept alive by nostalgia. It is a precision microwave machine operating in a vacuum using an electron beam, a carefully engineered slow-wave structure, and voltages that would destroy ordinary consumer electronics. So, why did the transistor replace almost every vacuum tube but fail to eliminate this one completely? The answer begins with an apparent contradiction. To amplify some of the fastest radio waves used in modern electronics, engineers first had to find a way to slow the wave down. For the first decades of electronic history, vacuum tubes were not old-fashioned. They were electronics. A heated cathode released electrons into an evacuated glass or metal envelope. Electric fields guided those electrons toward other electrodes. Add a control grid, and a weak input signal could govern a much stronger flow of current. That made amplification possible. Voices could cross continents. Radio stations could reach millions of listeners. Radar receivers could detect faint echoes. Early electronic computers could switch between states thousands of times per second. The same basic family produced many specialized devices. Triodes amplified audio and radio signals. Magnetrons generated powerful microwaves. Klystrons amplified signals at frequencies where ordinary tubes struggled. Each device shaped an electron stream in a different way. Then the transistor arrived in 1947. Instead of controlling electrons inside a vacuum, it controlled charge inside solid material. The transistor did not instantly defeat every tube. Early transistors had their own limits, especially at high frequencies and high power. But for consumer electronics, the direction was unmistakable. Solid-state devices could be made smaller, run from lower voltages, survive mechanical shocks, and eventually be manufactured by the millions on integrated circuits. The vacuum tube lost the markets where size, cost, and efficiency mattered most. Yet high-frequency power created a different contest. Radar, satellite communication, and electronic warfare did not merely require a device to switch on and off. They often required a weak microwave signal to be amplified into a powerful, clean, wideband transmission. At those frequencies, every physical dimension mattered. Electrode spacing, transit time, heat, electrical breakdown, and the tiny capacitances inside a device could determine whether an amplifier worked at all. The traveling wave tube survived because it did not try to behave like an ordinary tube. Its practical story began during the Second World War, when radar engineering was advancing at a speed few peacetime laboratories could have matched. Britain had already helped transform microwave radar through the cavity magnetron, which could generate short wavelength radio energy at high power. Shorter wavelengths allowed smaller antennas and sharper radar beams, making airborne microwave radar far more practical. But generating a microwave signal and amplifying a microwave signal are not the same job. A magnetron is an excellent oscillator. It creates powerful microwave energy. Yet many systems also need an amplifier that accepts an existing signal, preserves the information carried by that signal and raises its power across a useful range of frequencies. A narrowband device may work beautifully at one frequency and poorly a short distance away. That is acceptable for some radars. It is much less useful for broadband communication, frequency-agile systems, or equipment that must respond across a wide spectrum. Inside this wartime world appeared one of the least likely inventors in microwave history. Rudolf Kampffner had been trained as an architect in Vienna. He was Jewish, and the rise of anti-Semitism drove him to Britain in the 1930s. There he worked as an architect while pursuing electronics as a serious private interest. After war began, his Austrian birth briefly made him an enemy alien in British eyes. He was interned, then released, and eventually entered a secret microwave research program. Kampffner was not the first person to imagine interaction between an electron beam and a traveling radio wave. Earlier experimenters, including Andre Heff in California and Niels Lindenblad at RCA, had explored related slow-wave concepts. But in 1942 and 1943, Kampffner developed the practical helix traveling wave tube that became the ancestor of the modern device. His surviving early sketch is dated November 12, 1942. The central idea looked almost too simple. Send a narrow beam of electrons down the center of a coil of wire. Feed the microwave signal into that coil. Allow the signal and the electron beam to travel side by side, interacting continuously along the length of the device. But there was a fundamental problem. The radio wave naturally moved far too fast. An electromagnetic wave in a wire or waveguide travels at a substantial fraction of the speed of light. The electrons in the tube, although moving extremely fast by human standards, were slower. If the radio wave rushed past them, the interaction would be brief and weak. The electrons could not transfer much energy to a signal that immediately escaped ahead. Kampffner's helix changed the geometry of the race. The radio signal did not travel straight down the tube. It followed the much longer spiral path of the wire. The wave still moved rapidly along the conductor, but its progress in the forward direction became much slower. By choosing the diameter and spacing of the helix, engineers could make the forward speed of the wave approach the speed of the electron beam. The wave and the electrons could now travel together. That synchronization is the heart of the traveling wave tube. At the entrance, an electron gun releases and accelerates a beam through a high vacuum. Magnetic focusing keeps the beam narrow as it passes through the center of the slow wave structure. The weak microwave signal enters the helix. Its electric field alternately speeds up and slows down electrons in the beam. At first, the electrons may be spaced almost evenly, but after some are accelerated and others decelerated, the faster electrons begin catching the slower ones. They gather into bunches. Those bunches then reach a phase of the radio wave where they give up kinetic energy to it. The microwave signal grows stronger as it travels down the tube. This is the part that makes the device so different from a conventional amplifier tube. The exchange does not occur at one grid or inside one resonant cavity. It continues along much of the tube's length. The electron beam and radio wave act almost like two travelers matching pace long enough to exchange energy continuously. To amplify a fast wave, engineers had deliberately slowed it down. Kampffner's first devices were experimental and imperfect. The traveling wave tube did not suddenly replace the magnetron or win the war in 1943. Its great impact came later. But the principle was powerful enough to attract John Pierce of Bell Laboratories, a mathematician and microwave engineer who recognized that Kampffner had found something extraordinary. Kampffner had reached the invention through physical intuition and experiment. Pierce supplied the theory that made systematic design possible. The relationship was later summarized in a famous line. Kampffner invented the traveling wave tube, while Pierce discovered it. That distinction mattered. A laboratory device can prove that a phenomenon exists. A mathematical theory can tell engineers how gain changes with beam current, voltage, frequency, helix geometry, and length. It can turn repeated trial and error into a design discipline. After the war, Bell Laboratories became one of the centers of traveling wave tube development. The timing produced one of the great ironies in electronic history. Bell Labs was helping perfect the specialized vacuum tube that would survive the semiconductor revolution. And Bell Labs was also the birthplace of the transistor that would destroy nearly every other vacuum tube market. The two technologies were not simply enemies, they were solutions to different physical problems. In December 1947, John Bardeen and Walter Brattain demonstrated the point-contact transistor under the direction of William Shockley. Pierce himself helped give the new device its name. Over the following decades, transistors conquered low-power amplification, switching, logic, consumer radio, television, telephony, and computing. A transistor could be tiny. A traveling wave tube could not. A transistor could operate from comparatively low voltages. A traveling wave tube required an electron gun and a carefully regulated high-voltage power supply. A transistor did not need a heater to release electrons from a cathode. A traveling wave tube did. Solid-state circuits could be integrated into chips. A microwave vacuum tube remained a precision assembly of metal, ceramic, magnets, electrodes, and vacuum seals. If the contest had been decided only by convenience, the traveling wave tube would have disappeared. But microwave power is not convenient physics. At low frequencies, the electric field inside a conventional tube can be treated as if it changes everywhere almost at once. At microwave frequencies, that simplification collapses. An electron may need a meaningful fraction of one radio cycle merely to cross the space between electrodes. By the time it arrives, the field may have reversed. The very capacitance between closely spaced metal parts can let the signal leak around the control element. Leads that once behaved like simple wires begin behaving like inductors and antennas. The dimensions of the device become part of the circuit. Shrinking a conventional tube helps only to a point. Smaller spacing increases the risk of electrical breakdown and makes heat harder to manage. Resonant cavity tubes, such as the klystron, solve some of these problems by replacing grids and wires with carefully shaped metal chambers. They can achieve enormous power, but the cavities naturally favor particular resonant frequencies. The traveling wave tube takes a different approach. Instead of asking one cavity to perform the entire exchange, it spreads the interaction along a path. That is why bandwidth becomes central to its survival. A radar or a communication transmitter does not always need only the loudest possible signal. It may need controlled power across many frequencies, with the waveform preserved well enough to carry data, measure distance, or create a believable electronic deception. At high frequencies, solid material imposes limits. Charge carriers move through a crystal lattice. Heat must escape through a compact semiconductor structure. High voltage can produce breakdown. Parasitic capacitance and inductance become increasingly significant as wavelengths shrink. Engineers can solve many of these problems, and modern gallium arsenide and gallium nitride devices are extraordinarily capable. But the vacuum offers its own advantage. Electrons can move through empty space without colliding with a solid lattice. A traveling wave tube uses that freedom at a much larger physical scale than a transistor. Its electron beam can carry substantial energy. Its interaction circuit can be engineered for broad frequency coverage. And because amplification occurs continuously along the slow wave structure, the device can combine high gain, high microwave output, and wide instantaneous bandwidth in ways that remain valuable. That does not mean every traveling wave tube is more powerful than every transistor amplifier. The comparison depends on frequency, bandwidth, efficiency, duty cycle, size, reliability, and cost. In many applications, solid state has already won. In others, Engineers use large arrays of semiconductor modules to reach the required power. But in demanding corners of the spectrum, especially where high power and broad bandwidth must exist together, the traveling wave tube remains difficult to displace. Its first great post-war expansion came not from weapons, but from communication. Microwave relay networks carried telephone calls and television signals between towers across long distances. A useful relay amplifier had to strengthen a signal without destroying the information encoded in it. The wide bandwidth of the traveling wave tube made it attractive. Then engineers looked upward. On July 10, 1962, Telstar 1 entered orbit. The small experimental satellite helped relay television, telephone, and data signals across the Atlantic. Its transponder received a microwave signal from Earth, shifted its frequency, amplified it, and transmitted it back down. At the center of that chain was a traveling wave tube. The satellite itself produced only a small amount of electrical power. Its transmitter output was tiny compared with a terrestrial broadcast station. Yet from orbit, that amplified microwave signal helped create the first live transatlantic television transmissions by satellite. A device born in a wartime radar laboratory had become part of the infrastructure that made the planet feel smaller. Communication satellites became one of the traveling wave tube's strongest territories. A satellite power amplifier must operate for years without repair. It must survive launch vibration, vacuum, radiation, and wide temperature changes. It must convert limited onboard electrical power into a dependable radio frequency signal strong enough to reach Earth. Traveling wave tube amplifiers, usually called WWIIs, evolved into compact systems containing the tube, a high-voltage electronic power conditioner, protection circuits, and often linearization electronics. Engineers improved cathodes, magnets, helix supports, thermal control, collectors, and manufacturing cleanliness. The old image of a glowing glass radio valve no longer described the machine. Modern space TWTs are often sealed inside metal structures. Some are no larger than a piece of laboratory equipment that could be held in two hands. Others are built for higher power. The vacuum is hidden inside. So is the electron beam. Nothing visible needs to glow. One of the greatest challenges is efficiency. After electrons transfer part of their energy to the microwave signal, they still reach the end of the tube carrying unused kinetic energy. Simply smashing them into a collector wastes that energy as heat. Engineers developed depressed collectors with multiple voltage stages. Electrons leaving the interaction region are sorted according to their remaining energy and collected at different electrical potentials. Part of their energy can effectively be recovered, improving overall efficiency and reducing waste heat. That refinement matters enormously in space, where every watt is precious and heat is difficult to remove. The same basic technology has traveled far beyond Earth. New Horizons, the spacecraft that flew past Pluto and later Arrokoth, carries redundant traveling wave tube amplifiers for its X-band downlink. The power delivered to the antenna is only measured in watts, but the signal is engineered to cross billions of miles before enormous antennas on Earth recover the data. The survival lesson is easy to miss. The traveling wave tube did not remain important because it stayed unchanged. It remained important because engineers repeatedly rebuilt it for new missions. The helix traveling wave tube is only one form. A helix provides broad bandwidth, but the thin wire limits how much power and heat it can tolerate. For higher power applications, engineers can replace the helix with a chain of coupled cavities or other slow-wave structures. These versions often sacrifice some bandwidth in exchange for greater power handling. The result is a family rather than one object. Some TWTs serve satellite communication, others serve radar. Others operate in test equipment, high data rate links, or electronic warfare transmitters. Their dimensions, output power, frequency bands, and cooling systems may differ dramatically. What unites them is the same broad principle. An electron beam transfers energy to an electromagnetic wave while both move together through an interaction structure. And this is where the story returns to the battlefield. A modern aircraft faces a very different radar environment from the one Kampfner knew. Threat radars can search, track, guide missiles, change frequencies, and process signals digitally. Electronic defense systems must recognize those emissions, determine what kind of threat they represent, and respond quickly enough to disrupt the engagement. The response may involve noise, false targets, altered timing, frequency manipulation, or other techniques whose precise operational details are often classified. But almost every active jamming technique shares one requirement. The defensive signal must be transmitted with enough microwave power to matter. A weak imitation will not fool a radar receiving a strong echo from the actual aircraft. A jammer may need to cover a wide frequency range because it cannot assume every threat operates on one exact channel. It may need to change waveforms rapidly. It may have to fit inside an aircraft pod, a fuselage bay, or something even smaller. That combination of high power, high frequency, and broad bandwidth is exactly the territory where traveling wave tubes built their last fortress. A public example is the AN/ALE 55 fiber optic towed decoy associated with the F/A 18E and F Super Hornet. The system is designed to help defend aircraft against radar-guided threats. Part of the equipment remains on the aircraft, where sensors and processors analyze the electromagnetic environment. A small decoy can be deployed behind the airplane on a cable containing an optical fiber. The fiber carries information to the towed unit. Inside that unit, according to publicly available descriptions, are high-power traveling wave tubes used to amplify the signals it transmits. The concept is remarkable. Instead of placing every active transmission directly on the aircraft, the system can create a powerful radio frequency source at a distance behind it. If a radar or missile is deceived into treating that source as the more attractive target, the threat may be drawn away from the aircraft itself. The traveling wave tube does not think. It does not identify the radar, choose the deception technique, or calculate the false signal. Digital receivers, processors, and other solid-state electronics perform those jobs. The tube supplies power. This is the modern relationship between the supposed rivals. Transistors and digital processors create, analyze, and control the signal. The traveling wave tube performs the final microwave amplification when the design demands a combination of characteristics that vacuum electronics can still provide efficiently. The fighter is not carrying a museum piece from 1943. The device is a highly evolved descendant, built with modern materials, precision manufacturing, advanced power electronics, and decades of accumulated design knowledge. But the physics inside it would still be recognizable to Kampfner. An electron gun creates a beam. A slow-wave structure keeps a microwave signal beside that beam. Electron bunches give their energy to the wave. A collector receives what remains. The external package may belong to the 21st century. The operating principle was proven during the Second World War, and the F/A-18 example is only one visible piece of a much larger, mostly hidden landscape. Traveling wave tubes remain useful in certain radar transmitters because radar may require brief bursts of substantial power, frequency agility, or broad coverage. They remain common in satellite payloads because high-frequency communication links need efficient, reliable amplification. They appear in electronic warfare systems because a jammer benefits from power across a band rather than at one narrow frequency. Specialized vacuum electronic devices also continue to serve particle accelerators, scientific instruments, and deep space communication, although those systems may use klystrons, gyrotrons, or other tube families rather than TWTs. This distinction matters. The phrase vacuum tube covers many devices. A kitchen magnetron is not a traveling wave tube. A guitar amplifier triode is not a traveling wave tube. A medical accelerator may use a klystron or magnetron. They all move electrons through vacuum, but they organize the interaction differently. The traveling wave tube's special talent is not simply making a lot of power. Its defining strength is amplifying a microwave signal over a useful bandwidth while preserving the controlled information or waveform carried by that signal. That makes it especially suited to systems that must communicate, measure, or deceive. But semiconductor technology has not stopped advancing. Gallium arsenide allowed solid-state microwave amplifiers to operate far beyond the capabilities of early silicon. Gallium nitride raised the stakes again by tolerating higher electric fields, higher power density, and higher operating temperatures. Active electronically scanned array radars distribute transmission across many small solid-state modules. If one module fails, the radar may lose only a small fraction of its total performance, rather than losing one central transmitter. Solid-state power amplifiers can start instantly, operate from lower voltages, fit naturally into modular architectures, and avoid cathode wear. In many frequency bands and power levels, they have already replaced microwave tubes. So, why has the traveling wave tube not vanished? Because replacement is not decided by one specification. Imagine two amplifiers. The first is solid-state, compact, modular, and easy to control, but needs many combined devices to reach the desired broadband output. Combining those devices adds losses, weight, cooling, and complexity. The second uses a high-voltage electron beam and demands careful vacuum engineering, but produces the needed microwave power across the band in one amplification chain. The better choice depends on the mission. On a large ground radar, size may be less important than peak power. On a satellite, efficiency and mass may dominate. On an aircraft jammer, bandwidth, power density, cooling, and response speed all compete. On a phased array radar, distributed solid-state modules may be ideal. On a broadband electronic warfare transmitter, a TWT may still offer the more practical answer. Engineers do not award technology victories for elegance. They select the device that closes the system-level trade. Sometimes the winning design is a hybrid. A microwave power module can use solid-state electronics to generate and preamplify a precisely controlled signal, then pass it to a miniature traveling wave tube for the final power stage. The semiconductor handles the intelligence. The vacuum tube provides the muscle. A compact high-voltage supply links the two. That arrangement captures the real outcome of the transistor revolution. The transistor did not merely fight the tube. It also made the surviving tube easier to control, more efficient to power, and more useful inside sophisticated systems. The technologies that appeared destined to eliminate each other became partners. There is another reason the traveling wave tube remains difficult to replace. Building one is an extreme manufacturing problem. The electron beam must remain narrow without striking the interaction structure. The helix or cavity chain must hold dimensions accurate enough for microwave operation. Materials must survive heat and high electric fields. Vacuum seals must remain sound for years. Cathode chemistry must be consistent. Internal surfaces must be clean because microscopic contamination can shorten life or trigger electrical breakdown. In a space-qualified device, a defect cannot be repaired after launch. In military equipment, the tube may experience vibration, temperature cycling, and long storage followed by immediate demand. Reliability is not created by the word vacuum. It comes from painstaking control of materials and process. This is one reason the industry became specialized. When consumer tube factories closed, not all of their knowledge was relevant to advanced microwave tubes, but the broader manufacturing base narrowed. Modern TWT production belongs to a relatively small group of companies and government-supported laboratories with expertise that can take years to develop. At the same time, research continues. Engineers are exploring new slow-wave structures made with precision machining, microfabrication, and additive techniques. They are pushing vacuum electronic devices toward millimeter wave and sub-terahertz frequencies where generating useful power becomes increasingly difficult. Some experimental designs replace the classic helix with folded waveguides, coupled cavities, metamaterial-inspired structures, or circuits built at microscopic scale. The vacuum tube did not freeze in 1943. It followed the frontier upward in frequency. That creates the final tension in the story. Gallium nitride continues to improve. Solid-state arrays continue to grow more powerful. Better combining networks, cooling, packaging, and digital control keep taking territory from tubes. At some point, a semiconductor solution may become superior in a mission that once required a TWT. But the target is moving. Radar and communication systems demand wider bandwidth, higher data rates, higher frequencies, more power, and smaller packages. As solid-state advances, vacuum electronics advances too. A device can lose old applications while finding new ones at frequencies where semiconductor power is scarce. There may never be a single day when engineers declare the traveling wave tube dead. It may simply retreat again into narrower but more demanding territory. That is exactly how it survived the first time. The transistor conquered the enormous world of ordinary electronics. It made pocket radios possible, enabled digital computers, and transformed civilization. The traveling wave tube did not challenge that victory. It abandoned the battlefield where the transistor was strongest. It moved into radar transmitters, satellite payloads, deep space links, and electronic warfare systems that most people would never open, repair, or even see. There, size was not the only measure of progress. A device could be larger and still be better. It could require a vacuum and still be more practical. It could use a heated cathode and still belong inside a modern system. It could trace its operating principle to a wartime laboratory and still perform a task that the newest semiconductor technology had not fully taken away. Rudolf Kampfner began as an architect. His great electronic invention was also an act of architecture. He arranged a path for a wave, a path for a beam, and a structure that allowed the two to remain together long enough to exchange energy. The helix did not merely carry the signal. It controlled time and distance inside the tube. It made the wave appear slower in the direction that mattered. That single geometric decision turned an electron stream into a broadband microwave amplifier. The machine later crossed oceans through relay towers, carried television through Telstar, sent data home from deep space, powered radar and communication links, and entered electronic defenses designed for aircraft that fly faster than sound. That is why the title requires one important word. Transistors did not fail to replace vacuum tubes. They failed to replace them fully. In almost every device people touch, solid state won. But wherever engineers still need a rare combination of microwave power, frequency, and bandwidth, the traveling wave tube remains a candidate, and sometimes the best one. Its survival is not proof that old technology is secretly superior to new technology. It is proof that technology does not advance in a straight line. A new invention can dominate the world without erasing every specialized strength of what came before. The vacuum tube survived by becoming almost invisible, not in living room televisions, but behind antennas, not in desktop computers, but in satellite transmitters, not in corner drugstores, but in laboratories, radar systems, spacecraft, and electronic countermeasures. The glass bulb disappeared from daily life. The electron beam did not. And more than 80 years after a displaced architect drew a helix around that beam, the wave is still traveling. If you found this hidden connection between World War II engineering and modern technology fascinating, subscribe for more stories about the machines, materials, and forgotten inventions that shape the world we still live in.